At high frequencies, even extremely short wires are going to begin to exhibit a wide variety of parasitic effects. And because of this, microwave and other high frequency circuits, they're almost never constructed using standard breadboarding methods such as through-hole or your proto boards that you're used to using in the labs. Instead, they're almost always constructed out of small, flat circuit boards that use microstrip transmission lines as the interconnect layer. In fact, the parasitic behavior of wires will often dominate circuit behavior, meaning that it is actually physically impossible to get microwave circuits to work appropriately if you were to try to breadboard them. And so if you're a microwave engineer, a lot of times you go from simulation straight to a printed circuit board solution. So what I'm showing here on this slide is a cross-section of a microstrip transmission line on the top here, and then I'm showing a bird's eye view of some microstrip down here on the bottom. So let's focus on this top image right here. On the bottom of a microstrip board, which is typically called the substrate, we've got a continuous sheet of metal. Usually this is copper, it could be aluminum, but the point is that it's continuous. It's a solid sheet of metal, and it's called the ground plane. That ground plane has been attached to a insulator, usually a rigid insulator, and it's a dielectric material, right? So we're concerned with its electric permittivity. And it's got a certain thickness to it. And then on top of that is a second layer of conductor. And again, typically that's copper. Typically it's very thin. And this top layer of copper has been patterned into narrow ribbons of metal, and they've been patterned to form circuits, and these are called the signal lines. So this combination of a ground plane, the dielectric material, and the signal line, those three things together are what form up a microstrip transmission line. So far we've been dealing with coaxial transmission lines, and now we're moving on to microstrip T-lines. So we know that the most important function of the important parameter of a T-line is its characteristic impedance Z0, and Z0 for a microstrip T-line, it turns out that it is a function of the width of the signal trace, the thickness of the dielectric substrate, and the relative electric permittivity. So these are going to be the variables W, H, and epsilon R. Those are going to be the variables that we'll see later on in the class that drive what Z0 is. To fabricate these printed circuit boards, basically what's happened is we take a thin dielectric material, usually fiberglass. We coat both sides of it with a thin layer of copper. We then use a chemical called photoresist. We apply it to the top of the board. The photoresist is light sensitive, and we then put an image. We pattern an image into it using lenses and reducing masks. That allows us to chemically etch away copper, removing the copper that would have been here and the copper that would have been here, and only leaving the copper that's left in the middle. And this is called patterning. This picture on the bottom of the screen is an example of some T-line that has been patterned, so it's not always just rectangular. We can see that the T-line over here is thin, and then it gets wider and extremely narrow in the middle. Believe it or not, what I'm showing here is a fourth order microstrip low pass filter down here. So we'll find out in the class that you can actually design L's and C type circuits, passive circuits, using nothing but copper layer on microstrip, which is kind of an interesting application of microstrip design. But that's just a little bit of a teaser. We're not quite ready for that type of information yet. So as I said on the last slide, the properties of the microstrip T-line, the important properties, are dependent on the width, the height, and the epsilon R. So we're going to talk about all of these in a little bit more detail next. What I'm presenting here is we're going to talk about the substrate material, and again, the substrate is the dielectric material that the Microstrip T-line is built on. An example of a common substrate is, you may have heard of the term FR4 before. So in this table, the first column that I've got here, it lists just the type, which would be the common industrial name of it. So Duroid 5880, FR4, TMMM6, stuff like that. You've probably heard of some of these already. And so now you know that those industry names refer to common substrates that transmission lines or printed circuit boards can be manufactured from. The next column that we have is the relative permittivity of the dielectric material. You can see that the dielectric material of Duroid is made of fiberglass and Teflon mixed together, and it has a relative electric permittivity of 2.2. And this table is arranged in increasing dielectric constant here. By increasing this relative permittivity or increasing dielectric constant, the propagation velocity of the wave along the transmission line is going to decrease, meaning the wave is going to physically travel a little bit slower. And since we now know that frequency is fixed, it means the wavelength of the signal in the T-line must decrease. So what I'm saying mathematically is that we know that the propagation velocity of a wave traveling in a conductor is, or any material, is equal to 1 over mu epsilon. And so this would be the magnetic permeability of the conductor, and this is the electric permittivity of the insulator. So in this formula, if the relative, as ER increases, as this number goes up, since it's in the denominator of the fraction, propagation velocity is going to go down. So signals are fast in Duroid and they're slow in TMM10I, right? Additionally, what we would say is, since the propagation velocity is equal to the wavelength times the frequency, F is fixed, we now know, by the signal source, either the transmission or the reception signal source, and if mu p is decreasing, that means, since this is fixed, this has to decrease proportionally to mu sub p. So what we're saying is that as we get larger and larger relative dielectrics, the wavelength of the signal traveling in the microstrip T-line has to decrease. So for the same frequency signal substrate with high electric permittivity, we have shorter wavelengths than substrates with low electric permittivity, which means we can make them with smaller features. So the higher the dielectric constant, we can tend to get away with making smaller features on those printed circuit board materials. The second column that I've got here is called the loss tangent, tan delta loss tangent. And this is a measure of how lossy the dielectric is. And the definition of loss tangent is that the tangent of delta is equal to the effective conductivity of the T-line over omega angular frequency times electric permittivity. We'll talk about this more, so don't worry, I'm just giving you a little intro. The lower the loss tangent, that means that the insulator material is a better insulator. However, they typically cost more as well. There are other properties other than epsilon r and loss tangent that affect microwave circuit performance, and that's temperature, which is going to impact the dielectric constant, and the loss tangent. The material that the circuit board is made out of also is going to have some influence on the physical properties of the circuit board in terms of flexibility. Some of these materials are extremely brittle and difficult to mill with and to use in actual manufacturing systems, and they're not particularly rugged. So if you're going to build something out of it and then put it in a product that needed to be ruggedized, they wouldn't be good choices. And then some substrates aren't suitable to certain environmental conditions. They could oxidize or absorb liquids or things like that. So Let's move on to conductors, and the primary thing that we're concerned with when we talk about the conductor on a microstrip transmission line is the specification of the copper cladding on the top and the bottom of the microstrip board itself. So we're talking about this material here and here on the microstrip. And this is usually specified in something called deposition weight, and commonly you'll see something like 0.25 ounce copper board, or 0.5 ounce copper board, or 1 ounce copper board. So what are they saying? Deposition weight, what this means, 0.25 ounce, means that they've applied 0.25 ounces of copper evenly per square foot of surface area. So they've taken by weight a 1/4 ounce of copper, and they've spread it perfectly flat, or as flat as they can, over 1 square foot of the substrate material. So what that translates to is for fixed metals, that translates to a common thickness. So for example, 1 ounce is 1.4 mil. Half ounce is 0.7 mil. Etc. 1/4 ounce is 0.35 mil. So, and if you're not familiar with mils, 1 mil is just 1,000th of an inch. It's a unit commonly used in American manufacturing. So if I divide an inch by 1,000, I get a mil. One thing to notice is that these measurements are for copper only. Other materials are going to have different thicknesses at same deposition weights. For example, gold has a much higher atomic weight than copper, which if I were to apply 1 ounce of gold to a printed circuit board, I'm going to have a much thinner surface layer than a 1.4 mil. I don't know that figure off the top of my head, but I know it's going to be thinner than 1.4 mil. So by increasing the weight of the copper, obviously I'm increasing the thickness. So what are the advantages and disadvantages? Well, increasing a thickness is going to make the circuit more physically robust, and it's also going to reduce the ohmic losses of the traces. It's going to reduce the series resistance of the trace. However, this is also going to come at the expense of an increase in conductance. Also, we need to recall that the equations we developed for transmission line analysis for R prime, G prime, L prime, and C prime, these all assumed that the skin depth was much smaller than the metal thickness. So we need to make sure that stays true. And very thin copper weights may violate this assumption, so you always need to check that. One negative effect of lots of copper is it's what's called a sidewall effect. If I make extremely thick copper traces, what ends up happening is if this is copper and this is copper, I get a parasitic capacitor right there. I also get a parasitic capacitor here and a parasitic capacitor here, where I can minimize that effect with thinner copper traces. The capacitor here and the capacitor here are effectively eliminated because there's not enough cross-sectional area to support them. So thick sidewalls can negatively affect circuit design because of these parasitics. Here I'm showing different topographies of surface roughness of the different materials that have been applied to circuit boards. And so this RA number just is we don't have to know exactly what it is, but the bigger the number, the rougher the surface. So kind of the opposite of sandpaper. So rough copper surface, like we're showing here at 560 nanometers, these valleys and peaks on the surface will act as radiators, and meaning electromagnetic energy is actually going to be ejected from the board at these peaks. It's not substantial, but it does happen. The best way to eliminate this behavior is by using a much smoother surface on your printed circuit boards. So these topographies can really influence circuit performance, in particular rough copper acting as radiators. So in general, a smoother copper surface is better, and as most things, you pay for quality, and having a 112 nanometer copper board is going to be much more expensive than having a surface roughness of 560 nanometers. Now let's move on and take a look at some of the effects of microstrip geometry. Here I'm showing a typical cross-section for the microstrip geometry, for the microstrip circuit. I've got the signal path, I've got the ground plane. In between, I've got the dielectric material with electric permittivity epsilon R. What you'll notice, though, when we draw the field lines for when an electric signal travels along this signal path, what is established is an electric field between the signal path and the ground plane. Now, some of those electric field lines are fully contained within the dielectric, these ones that are purely vertical here. However, there is going to be some electric field that leaves the top of the signal line and bends down through the dielectric material to the signal plane. And so what is happening here is these signal paths see an inhomogeneous material. They first go through air and then they go through the dielectric material. So this inhomogeneous dielectric means that the EM waves propagating in a microstrip transmission line aren't going to behave exactly as our earlier models predict, because we had always used a solid surface or a continuous surface of dielectric material. And here we've got an electric field that sees two different dielectric. There's an ER for air here, and then there's an ER for whatever the substrate material is. So to compensate for this effect, it's typical to model microstrip as a signal line that is completely buried in a continuous dielectric material that has an effective electric permittivity. And we call that just, instead of E sub R, we call it epsilon sub F, EFF, as shown in this bottom figure here. What the effect is going to be is that the wavelength in a microstrip signal is going to be different than what we would normally calculate with the equations that we've already developed for microstrip T-lines. And we give it a new name. We give this wavelength for electromagnetic wave in microstrip a new wave. It's called the guide wavelength, and it's given the symbol lambda sub g. And it's calculated just by taking what the wavelength would be in free space. So remember that we can calculate the wavelength of an electromagnetic wave in free space divided by taking the speed of light and dividing by the frequency. We take that and then we divide that quantity by the square root of this effective electric permittivity constant here, epsilon effective. And so this is whatever the free space wavelength is divided by effective electric permittivity, and that lambda is just free space. So that also means that the signal's traveling slower in the T-line than we would normally predict, and so what we have to do is to calculate the propagation velocity of the transmission line, we take C and we divide it by the square root of epsilon effective. And this is also going to change our calculations for beta. Beta becomes 2 pi f over mu p, where the mu p in this equation has to be calculated using this effective electric permittivity. So the exact method for solving for epsilon f in this situation is pretty far beyond the scope of the class. I'm just going to present the solution, an empirical solution for effective electric permittivity, and it is epsilon effective is equal to the relative permittivity, epsilon r, plus 1. Take that quantity, we divide it by 2. We then add to it the relative permittivity of the dielectric substrate, minus 1, and we divide that by the quantity 2 times the square root of 1 plus 12, and then we need to divide or multiply 12 by the H to W ratio of the microstrip T-line. Remember, this here is H and that is W right there. So the thickness of the substrate is H and the width of the transmission line strip there is W in that equation. You might also expect that this effective electric permittivity here is going to change or have an effect on our calculations for Z0. And it turns out that is the case, but the situation is a little bit more complex than it was for guide wavelength and propagation velocity and wave number here. It turns out that the microstrip trace acts as a modified parallel plate conductor, and therefore the analysis and design equations become controlled by the ratio of the trace width here to the height of the dielectric material, and we have to employ an approach called binning, where we apply different equations for different regimes. And in the calculation and analysis of Z0, what we'll do in later slides is we'll show some equations that we apply for different regimes of W to H ratio. So we'll look at the W to H ratio. If it's less than 1, we'll use one set of equations. If the WH ratio is greater than 1, we'll use another set of equations. And these are the analysis equations, or the equations that allow us to determine impedance of a known geometry. And then we'll apply a similar method to the design of traces. There's one last important thing that we need to know, though, before we get into the calculations of characteristic impedance of microstrip transmission lines, and that is that the microstrip transmission line itself has a maximum operating frequency, and this is limited by loss and a couple other factors. And the calculation that we'll perform to determine the maximum signal frequency that a T-line strip can use, that's the speed of light divided by 4 times h times the square root of the relative permittivity of the dielectric material. So this here is the maximum signal frequency that a T-line can possibly support. And we see that that really is a function of the substrate material right there.